The initial design utilized 4 separate delay lines with feedback loops to produce the desired clock speed. The selectable speeds were 12.25 nanoseconds for fast clock, 12.5 for normal, 12.75 for slow, and 13.8 for super slow. With the advent of the Cray 1S, the delay line clock for normal speed was replaced by a crystal. This produced improved stability under normal running conditions. The other 3 clocks continue to be controlled by delay lines. All clock speeds remain the same. With the advent of the Cray 1M, all delay line clocks, except for the super slow speed, were replaced by crystals. If used in a Cray 1S, the crystals are selected to produce the same clock speeds previously described. If used in a Cray 1M, different crystals are inserted to produce the slightly faster 1M clock speeds. The clock speeds shown are for the Cray 1M. Now let's take a look at the block diagram for each of the 3 possible clock circuit variations. The block diagram shown reflects the initial clock design. The TZ module in location F4 performs 3 functions. Based upon the speed select switch on the power distribution unit, one of the 4 clock speed circuits is activated. The symmetrical output of the selected delay line oscillator then passes through a pulse shaping circuit which produces the wave shape shown. The wave shape reflects the normal clock speed. If another speed were selected, the 8.5 and 12.5 nanosecond periods would vary. The resultant clock pulse then passes through a 1 to 64 fan-out and is fed to the output of the module. The 9 TC modules fan out the master clock to the 4 CPU columns, or to a total of 576 modules. Each TC module receives 2 copies of the clock and provides 64 outputs. If we multiply the 9 TC modules times 64 copies each, we arrive at the required figure of 576. The 36 ZC modules fan out the master clock to a maximum of 8 memory columns, or to a total of 1,152 modules. Each ZC module receives 1 copy of the clock and provides 32 outputs. By multiplying 36, the number of modules, times 32, the number of outputs per module, we arrive at the required figure of 1,152. You'll note that only 54 of the 64 TZ module outputs are used. Now let's take a look at a block diagram for the revised master clock, which came about with the advent of the Cray 1S. Note that a TO module was added, and ZO modules were used in place of ZC for fan-out to memory. The TO module contains a single crystal used to generate the normal clock. Its output wave shape is as shown. The circuitry on the TZ module, which previously generated the normal clock, was disabled and the input from the TO module used in its place. The TZ module continues to provide wave shaping and fan-out, and its output was consistent with the original design. It also continued to be the source of the margin clocks using the original delay circuits. Replacing the ZC module with ZO modules had nothing to do with the master clock. Both ZC and ZO modules, along with providing clock fan-out, were memory storage modules. With the advent of the expanded Cray 1S memory, from 1 to 4 million words, changes were made to the storage section to accommodate additional address lines and new memory chips. ZO was the resultant revised module designation. The most recent change to the master clock occurred with the advent of the Cray 1M, although the resultant design is compatible with previous models. The TM module, which replaces the TZ and TO modules, contain crystals for all but the super slow clock speed, and for the Cray 1M, a 12 nanosecond output rather than 12.5 nanoseconds. All other aspects of the module are identical to those previously discussed. For 1M systems, a YB module replaces ZC or ZO modules for fan-out purposes. Only 68 Cray 1 memory modules require a copy of the clock, so less fan-out is needed. Now let's take a closer look at each of the clock modules, starting with those associated with the initial design, TZ, TC, and ZC. Starting with the TZ module, you'll remember it performs three basic functions. They are: select one of 4 delay line oscillators depending upon the position of the speed control switch on the power distribution unit. As shown, the oscillator output is symmetrical. It assumes the normal clock speed was selected. Its second function is to reshape the oscillator output. The new wave shape is shown. Its last function is to fan out the clock, producing a total of 64 copies. The first circuit we'll look at is that of the oscillator. Depending upon the position of the speed select switch on the power distribution unit, P0 and P1, one of the 4 top circuits will be selected. For demonstration purposes, let's assume that the normal clock is selected, P0 and not P1. The output speed or cycle time would then be controlled by the delay of the highlighted circuit. The not T10 and not T12 gates produce a 2 nanosecond delay, 1 per gate. The 25.5 inches of foil between gates produce a 4.25 nanosecond delay. Remember that 6 inches of foil produces 1 nanosecond delay. The total circuit delay is therefore 6.25 nanoseconds. It causes the selected circuit to have an on time of 6.25 nanoseconds and an off time of 6.25 nanoseconds. The resultant wave shape is shown. It will now be sent to the pulse shaping circuit. The output wave shape of the pulse shaping circuit, T5, is also a function of circuit delay. When T10 goes to a 1, T5 immediately goes to a 1. It will remain a 1 for 4 nanoseconds, or until the zero output of not T6 passes through the 18 inches of foil and the T5 gate. The resultant wave shape is as shown. It is now sent to the fan-out circuitry. The fan-out circuitry is rather straightforward. It's done in 3 stages. The T5 output of the pulse shaping network drives 4 gates called B0. The Boolean equation for the B0 terms are shown just below the gates. All 4 outputs have the same name because they are driven by the same term. The number 4 to the left of the equation indicates 4 copies. Each of the 4 B0 terms then drive 4 gates producing 16 C0